Greetings, isang pagbati na puno ng kaalaman. For today, we will be dealing with beam deflections, and this is a several-part lecture on beam deflections, but today, we will be talking about one method first. This is the double integration method. This is lecture number 17. Now, why is it important for us to be able to understand beam deflections? Now, remember that beam deflections are actually the deformations of your transverse loads, transverse members, such as one of the most important structural elements, beams. Now, of course, it's important for us to be able to determine the maximum deflection or the allowable deflection in order for us to find the maximum allowable load that our structure can carry. Of course, look at this comic strip over here. Ayaw naman natin na ang pag-measure natin kung kailan mag-fail or magko-collapse ang ating structure is through trial and error. Okay? So, kailangan mahalaga na before even constructing our beams, our structures, our structural elements, it's important na alam natin, kaya nating i-design yung geometric properties at malalaman natin yung allowable load na kayang i-carry ng beams natin. So in ES 102, we will only be dealing with two of these most commonly used methods in solving beam deflections. For ES 102, we will be dealing with the double integration method and the area moment method, but with emphasis on DIM or the double integration method. The rest of these equations, the rest of these methods over here will be discussed in your succeeding structural engineering course, which is CE 18. Okay? Now, it is important for us first to derive the governing equation for what we call the Euler-Bernoulli beams. Now, take for example this simply supported beam subjected to transverse loads as shown. Now again, we have defined our neutral axis as the axis or the surface wherein there is no deflection at all. Now, once I apply these transverse loads, this is what the beam looks like. This is what the neutral axis looks like. Now, this is what you call the elastic curve. Now, the elastic curve is the single defining line in order for us to be able to describe the behavior of the entire beam. So once we know the equation of this elastic curve, we now know the behavior of the entire beam. Now, the elastic curve is a simplification of the entire structure, meaning if we want to get deflections or slopes at different points in the beam, we are only to observe the elastic curve. Now, please remember that our goal in the double integration method is find first the equation of the elastic curve. If we do not know the equation of the elastic curve, we won't be able to determine the deflection of any point along the beam and the slope at any point along the beam. Now, just as an introduction, this slide is not important for DIM. It's much more important for your area moment method. What I like about the double integration method is that it's actually quite mechanical as opposed to your AMM or your area moment method. That's why most students actually prefer using the double integration method over the area moment method. Now, if the elastic curve seems difficult to establish, it's suggested to draw the moment diagram of the beam first, meaning based on imagination, based on your engineering intuition, if hindi natin kaya agad-agad na malaman yung itsura or what the elastic curve looks like, we can always draw the moment diagram. But then again, well, it's not that important for DIM. Mas mahalaga ito. It's much more important when we are using the area moment method. Now, let's try to derive the governing equation for your elastic curve. Take, for example, this same simply supported beam, and I consider a differential element, a differential portion of the beam having length L. Now, before the deformation or the deflection occurs, this is what the portion of that beam looks like. And again, I am only interested in the neutral axis as it describes the entire behavior of the beam. Okay na yon. Now, for example, once the beam bends, this is what your beam looks like. Once the beam deflects, you should know that if I have downward forces as shown, what will happen is the top fibers will compress and the bottom fibers over here will elongate. However, please remember that the length of the neutral axis will not change. Okay. So let's try to understand the following formulas used in the derivation of our Euler-Bernoulli beams. Now, for example, look at this. Okay? Using your arc length formula, I know that the length L of the neutral axis, if it rotates or if the origin of my arc is this point over here, using our arc length formula, S equals R theta. So I can say that the length L is equal to rho theta. That's equation number 1 over here. Then, similarly, if I have any arbitrary point, I can find the arc length by saying that, for example, if I am considering the outermost fiber, L plus delta is just equal to rho plus C times theta. So that's equation number 2. Now, what I want to do here is to solve for the equations, the first and the second equations in terms of theta, okay? Such that if I now cross multiply, ibaba ko po, okay? So theta is just equal to L over rho, okay? That's for equation number 1. Then equation number 2, theta is equal to, ibaba ko itong rho plus C, L plus theta all over rho plus C. Then I cross multiply this equation, L rho plus LC is equal to L rho plus delta rho. Now I can cancel L rho on both sides of the equation, and I now arrive at LC is equal to delta rho. Okay? Then I further rearrange this equation. Okay? I divide rho, baba ko yung rho dito, then ibaba ko ulit yung L sa kabila naman. I have C all over rho is equal to delta over L. But remember, what is delta over L again? From our first long exam coverage, I know that delta over L is equivalent to the axial strain epsilon. Okay? Now, remember that one of the first assumptions in using the Euler-Bernoulli beams, the equation for your Euler-Bernoulli beams is that the material is elastic such that Hooke's law applies. And we know that Hooke's law is just equal to sigma equals E epsilon. And similarly, I can rewrite that equation as epsilon equals sigma all over E. Now, how did the beam deflect? It is due to the effect of the transverse loads. And again, from our second long exam coverage, we learned that your transverse loads cause flexural fiber stresses such that sigma is equal to my over I, or in this case, mc over I. Remember, c is the distance from the neutral axis to any distance, to any point in the beam. In this case, C is just equal to the distance from the neutral axis to the extreme or the farthest fiber. Then, what I can do is, I know that strain is epsilon equals sigma all over E. But sigma, as mentioned in the previous step, is just mc all over I. Therefore, I can say that epsilon is mc all over IE. Now, that equation can actually be equated to another one. I know that epsilon is mc over IE, but then again, epsilon, as we have shown before, where is that? This one over here, epsilon is also c over rho. So I can say that c over rho is equal to mc over IE or mc over EI. Now remember, EI E is the Young's modulus, and I is the moment of inertia. EI, if I multiply the two, is what we call your flexural rigidity. Okay? So I can cancel C here. I can cancel C here. It's present on both sides of the equation. Okay? Such that I now have 1 over rho is equal to M over EI. Now, 1 over rho is what we call the curvature at a point. Rho is the radius of curvature. And M, please remember, as always, is the internal bending moment. And E is the modulus of elasticity of the beam. And I is the moment of inertia of the cross section. Okay? Now, we won't derive it anymore, but kailangan yung manalig sa akin that for a given curve, the curvature, if you look at your Lighthold or your any calculus book, okay, 1 over rho is given by this equation. But then again, in ES 102, we are only dealing with very small displacements. Well, not just in ES 102, but at the end of the day, our goal is to have unnoticeable displacements, very small displacements, unseen to the naked eye even, such that the deflection, y, and the slope is very small, okay, such that I can say that if dy over dx is very small, okay, dy over dx squared is just approximately equal to 0. Something small, if I square it, it's approximately equal to 0. Okay? Such that what happens is if dy over dx squared is equal to 0, okay, so what happens is this is now 1 plus 0 raised to 3 halves. Okay? I have 1. Therefore, I can say that 1 over rho is d squared y over dx squared. And again, from our previous equation, from our previous slide, we have shown that 1 over rho is equal to m over ei. Okay? Now, m is just equal to ei d squared y over dx squared. Ito na yung mahalaga. This is now the differential equation for the elastic curve of the beam. Yung pala, when we want to find the deflection of a beam, when we want to find the equation of the elastic curve, okay, we have or we need to solve a differential equation. Okay? So this is the governing differential equation for your elastic curve. Now, let's try to analyze that differential equation. Now, sabi natin, from the previous slide, moment is just equal to ei d squared y all over dx squared. Now, here is the magic why it's called a double integration method. Because once I find, my first goal is to find the equation of the elastic curve, okay, which is this one over here, which will come from the moment function, which is this one. Then, kaya siya tinatawag na double integration, okay? Because if I integrate the moment function over here, d squared y over dx squared, I get dy over dx, okay, is equal to the integral mx over ei dx plus, please remember that if I integrate, meron po tayong constant of integration. Then, if I integrate further, okay, from the slope, I now get the deflection, okay, from your first constant of integration, c1x plus c2 naman. Okay? So it is first very important for us to get the equation, the moment function correctly before integrating twice. Once I now integrate twice, I now have the equation of the elastic curve. So ito na po yun. This is now the deflection of the beam or the equation of the elastic curve. Now, in other books, you will see that kung integration tong other side, if I differentiate naman, I get the shear. Okay? And if I differentiate further, I get the load. Now, in some books start with the load function or this one. Tapos, nag-integrate sila once, twice, thrice, then 4 times. But normally, that's actually not that logical because pag mali na, yung sa load mo, automatically, tuloy-tuloy mali na yan. So there's a bigger chance of committing mistakes if we start from the load. So in ES 102, it's okay to start with the moment function para at least, ma-minimize yung ating possibility of errors. So from the moment function, kailangan marunong lang tayong mag-integrate to get the slope, then to get the deflection. Now, going back to this slide, you can see that this is a differential equation, and if I integrate, there are constants of integration, C1 and C2. Now, how do I solve the constants of integration? From your subjects dealing with engineering mathematics, we know that in order for us to solve the constants of integration, I need to apply what we call a boundary condition. Now, what is a boundary condition? A boundary condition is a known set of values, right, for which we know the location and the behavior. So in ES 102, since we are dealing with beams, what are the boundary conditions that we know? Okay? Now, makakatulong dito sa boundary conditions, ang tinitignan po natin ay ang support reactions. In ES 102, we actually concentrate in boundary conditions 3, 4, and 5. So, iikot at iikot lang yung problems natin dito. Now, why can we use the support reactions as boundary conditions? As I have mentioned, boundary conditions are points where we have a known set of values or a known behavior. Now, when we say support reactions, we actually know the behavior of your support reactions. Why? Now, remember, if I look at boundary condition 3 and boundary condition 4, if I have a pin reaction or I have a roller reaction, we should know that the deformation, the deflection rather, right, is just equal to 0. Okay? Meaning, sabi nga natin, support reaction, wala pong deflection yan. Hindi gagalaw yung point na yan. Therefore, at the location where you have a pin and you have a roller, you can impose that delta or the deflection is equal to 0. Next, boundary condition. Pag meron kang cantilever or meron kang fixed support, okay? Pag meron ka pong fixed support, dalawa yung pwede nating impose na boundary conditions. I can impose that at the fixed end, at the fixed support, the slope is equal to 0 and the deflection is equal to 0. Now, what is the most common mistake that students commit? Please remember that you only impose slope, theta, equals 0 for fixed supports only. Okay? Kadalasan, kapag merong roller and pin ang ginagawa ng students, pinipilit din. Okay? They force that the slope is equal to 0. It's not. That's a very big mistake that students commit. Okay? So please remember that the only boundary condition we can apply in a pin and a roller is that the deflection is equal to 0. The slope is not equal to 0. Is that clear? I hope that's clear. Okay. Now, here are our sign conventions for a deflection if you get y. Okay? So, alternately, we use deflection as y or delta. If you get a positive value, meaning the elastic curve or the beam moves upward. If you get a deflection which is a negative value, okay, the deflection is downward. Now, how about for slopes, dy over dx or theta? Now, if I have positive to the right as my sign convention, right, as measured from the horizontal, we always measure the slope from the horizontal as such. If the rotation is counterclockwise, that's a positive slope. Okay? If it's clockwise, well, it's negative. But if we want our positive convention to be to the left, clockwise is positive and counterclockwise is negative. But in most of our problems, if not all, let's try to stick with this sign convention as to the right as positive. Okay? Para normal and easier lang lahat para sa atin. Okay? Now, I'd like to show you this example. This is actually not a part yet of the double integration method. I'll try to show you why it is important to use DIM, okay, by solving this example in brute force. Okay? Now, for the cantilevered beam as shown, loaded with a distributed load omega, we are being asked to determine the slope at the free end, which is this one, the deflection at the free end here, and the deflection at the midspan or the halfway through the beam. Now, take note that in the problem, they set the origin at the free end. So this is where my origin is, and to the right as positive. So what I do is, since I have a uniformly distributed load at any distance x, I should know that the moment function will not change, meaning it's just a function of x. We don't have any problem or any complication with the moment and your shear. Now, using your skills in solving internal bending moment, I can use equilibrium. I can sum moments about this point. Okay? I can say that mx plus, kasi po positive if I get the moment of this point, of this distributed load, omega times x, but I now converted that to a distributed load acting at the centroid. So omega x, yung equivalent load, multiplied by the lever arm x over 2 is equal to 0. Then I just transfer it to the other side of the equation to say that m of x is equal to negative omega x squared over 2. This is now the moment function. Then, from the moment function, I said that, again, don't worry, this is just an illustration. Hindi pa ito yung DIM na kailangan natin. This is just an introduction of how or why we need DIM and what's the easier step of solving moment functions. Okay? Then, next step, sabi natin, if I get the moment function, I integrate. In order for me to find the slope theta, if I integrate, I now have omega x cubed over 6 plus the constant of integration C1. I integrate further, double integration. I now have negative omega x to the 4th over 24, plus C1x plus C2. So the first equation is my moment function. Then I integrate, I get the slope. Then I integrate again, I now get the deflection. Okay. Now, after that, after integrating twice, I now need to solve the constants of integration. How again? By performing or by imposing your boundary conditions. Now, sabi natin, when we are using boundary conditions, I need to solve or I need to look for the support reaction. So the support reaction here is actually a fixed support. So that's boundary condition number 5 from the previous slide. And we know that if I have a fixed support, I can say that I can have 2 boundary conditions of fixed support. Since this is my origin 0, I can say that the deflection at the fixed support or the deflection at position L or the pinaka-end, the end of the beam is equal to 0. And similarly, aside from the deflection, the slope theta at the end of the beam, okay, at x equals L, since this is x equals 0, so at the fixed support at x equals L, the slope theta is equal to 0. So these are the 2 boundary conditions for a fixed support. Now, therefore, I can now say that if I substitute, okay, for example, here in my second equation over here, negative omega x is equal to L, okay, negative omega L cubed over 6 plus C1 is equal to 0. Okay? I solve C1 is equal to omega L cubed over 6. Then, I know that the deflection at L, so dito naman, sa third equation is equal to 0. So negative omega x is equal to L to the 4th over 24. Plus C1, we were already able to solve C1, omega L cubed over 6, times x, which is equal to L, plus C2 is equal to 0. Hence, C2 is equal to negative omega L to the 4th over 8. Now, once I now have the constants of integration, the problem now becomes easy to solve because I can just substitute the different values of x in order for me to find the slopes and the deflection. So since I now have C1 over here and C2 over here, okay, I can now solve the slope at the free end. So again, if I want to find the slope at the free end, I can use this equation over here. Okay? So that is x is equal to 0, correct? That is where my origin is. So I just substitute x equals 0 here, okay, and solve the problem. I now have omega L cubed all over 6. Don't forget, ibaba yung EI because I'm only interested in theta. So omega L cubed over 6 EI. You get a positive answer, meaning that is counterclockwise. Next, what is the deflection at the free end? So the deflection at the free end, I just substitute x is equal to 0 in this equation over here, right? So x equals 0. Why x equals 0? Because that is where the free end is. This is where my origin is. So I substitute x equals 0 here, substitute x equals 0 here, then ibaba ko po yung EI. I now have y is equal to negative omega L to the 4th over 8 EI. Well, it makes sense that the answer is negative, meaning the deflection is actually downward. So downward yung load, so you should expect that the beam will deflect downwards as well. What is the deflection at the midspan? So the midspan, so x is equal to, if the length of the entire beam is L, the midspan is x is equal to L over 2. So I substitute x equals L over 2 here. I substitute x equals L over 2 here. Okay? And ibaba ko yung EI, it's now negative 17 omega L to the 4th all over 384 EI. Okay? Now that's easy because the only load is a uniformly distributed load. But what if, okay, for example, okay, I change the type of loading and the type of support reactions? Okay, let's say I have a simply supported beam over here. Okay, it's still manageable. The moment function is still manageable because the load does not change. Meron lang support reaction na nadagdag. But what if I have a triangular load? The moment function is different from 0 to 2A, and it's also different from 2A to 4A. It's not a uniformly distributed load anymore. The behavior of the internal bending moment is now different because of the shape of your load. So mas mahirap. Now what if, hirapan pa natin. Okay, so imagine this is now the moment function. What if I have this type of load? Now it's different from 0 to A, it's different from A to 3A, and it's different from 3A up to 4A. So it's very difficult, very time-consuming for us to do all of this. Right? So you just table flip na lang if you see problems such as this. And it is very, very possible to have problems such as the ones na mahirap hanapan ng moment functions. So how do we deal with those? Right? There is what we call a discontinuity function. Now, this is very important in BIM, meaning mapapadali yung buhay natin if we know discontinuity functions and Macaulay functions. Now, meaning, for different types of loads, there is a discontinuity function. So, given an externally applied load or set of loads, depende lang kung what is the type of load, there is an equivalent discontinuity function. So, hindi na tayo mahihirapan. But before that, what I'd like to highlight here is this one. Right? For Macaulay functions, right, look at this box over here. Right? It's x minus a raised to n. That's a bracket. You don't immediately evaluate. Hey, now later on, if we substitute, I'll define the variables later. What I want to highlight here muna is that you don't immediately evaluate this one. Okay? What you do is, later on, if you have values, okay, for x and a, if x minus a is negative, okay, or the value inside the bracket is negative, your discontinuity or your Macaulay functions tell us that immediately that is equal, the entire thing is equal to 0. You don't need to evaluate. Example, x minus a is negative 5 raised to 2. You don't perform, you don't square, you don't raise it to n. Automatically, if this inside is negative, it's automatically, this entire thing over here is automatically equal to 0. But if x minus a is positive, you evaluate. X minus a raised to n. Example, x minus a is 5 raised to n, which is 2, for example. 5 squared, that's 25. Is that clear? So that is the takeaway from this slide. If this inside value of the bracket is negative, automatically this entire thing is equal to 0. Now, here are some properties of your Macaulay functions. You can go over it. These are just rules for integration and differentiation. It's actually just the same as what you do in calculus. So no worries about this slide. Now, these are the different discontinuity functions for different types of loading. Okay? So for ES102, we are only interested in the moment function. So these are all externally applied loads, 1 to 4. Let's start with the simplest. If I see a moment, a couple, an applied moment such as this, or a moment reaction, look at this. It is very, very important. Right? Look at the sign conventions. Right? For me to be able to determine the moment function, okay, the moment function of an applied moment or a moment reaction is equal to m naught, or the value of that moment, x minus a raised to 0. Okay? So let's first define m naught is the magnitude of that moment. Look at this. If this is clockwise over here, that's positive. Why? Because please remember that I am looking at the internal moment. So yung internal mo, pag clockwise po ito, the internal is counterclockwise, which is positive. So please be very, very careful. If the applied moment, again and again, common mistake, if the applied moment is clockwise, the moment function here is positive. X minus A, look at this figure over here. A is the location of the applied moment. Okay? Then raised to 0. Hirapan pa natin yung load. Let's make it more difficult. What if I have a concentrated load? If I have an upward concentrated load, right, M, the internal bending moment, M is equal to P, or the value of that load P, X minus A raised to 1. A is the location of that concentrated load. Now, what if the concentrated load is downward? Therefore, P here is also negative P. Okay? Next, let's make it more difficult again. What if I have a uniformly distributed load? Okay? M, the internal bending moment, is just equal to the magnitude, the intensity of that uniformly distributed load, omega naught, over 2. Okay? So please be careful. It's omega naught over 2. X minus A raised to 2. Okay? So I think you can see the progression. Raised to 0, pag moment, concentrated load, raised to 1, uniformly distributed load, raised to 2. Now, what is the value of A here? A is the start, is the location of your distributed load, or the location where the uniformly distributed load started. Okay? So, example, if this is the origin, the uniformly distributed load started at a distance A. Then the last type of load, yes, it's the last. Wala na pong any other type of loads that we will be dealing with. We will only be dealing with until a triangular distributed load or linearly varying distributed load. For example, so for example, I have a linearly varying load, a triangular load over here. The moment function is equal to m over 6. Now, what is m over 6? Please remember, m is not equal to the intensity. M is equal to the slope. So, m is equal to omega over b. So, omega is the magnitude or the intensity here, the largest one, divided by b. What is b? B is the distance, or the width, rather, of the distributed load. So, m is omega. So, this one, the height of the triangle, divided by b, or the base, the width of this triangle over here. So that's m all over 6. X minus a cubed. A again is the start, the location of the start of your triangular load. Okay. Now, please take note of all 4 of these. If you do not know all 4 of these, it's dangerous. Okay? So we need to memorize or know by heart these 4 moment functions over here to simplify our lives, para mapadali yung buhay natin. And please remember, right? Look at 3 and 4. There's a complication for 3 and 4. Note that for items 3 and 4, the distributed load should be loaded all the way up to the end of the beam for the moment function to be valid. Okay? So meaning it should be loaded up to the end. This should be loaded up to the end. Sir, what if it's not loaded up to the end? Invalid na po ba yung equation? Can't we use our equations anymore? Well, we can, but we need to perform what we call a dagdag bawas method. So I will be explaining later on what dagdag bawas method means. But then again, bottom line is, if the beam is not loaded up to the very end, you need to apply dagdag bawas method. And at the end of the day, after performing dagdag bawas method, you should only see shapes na rectangle rather, and a triangle. If the shapes are not rectangle and triangles, there's something wrong. And when we say triangle, it should look something like this. Okay? Bawal yung baliktad na triangle, meaning dito yung 0, tapos dito yung mataas. Well, you should see something that looks like this. Okay? So I'll show you dagdag bawas method later on. Okay. Now, just as a review again, okay, if you look at the moment functions, please know this by heart. K is the amplitude or the magnitude or the slope that depends on the type of your load. Okay? A is the location of the loading. It's positive if it is to the right of the origin. Otherwise, it is negative. Example, all of these are positive because if this is my origin, lahat sila, all of them are to the right of the origin. But if it is to the left, I can say that it's x minus negative a. Okay? Then n is the type of load. The type of load will determine the degree of the loading. 0 if that's an applied moment. 1 if that's a concentrated load. 2 if that is a uniformly distributed load. And 3 if that is a triangular or a linearly varying distributed load. Okay. Now, next, I'd like to highlight something and I'd like to show something. Given this simply supported beam over here and a concentrated load P, if I want to solve for the moment function, for example, okay, the moment function at section 1, at section 2, right, is R1x. At section 1, it's equal to 0. So that's just before, sorry, that's just before the support reaction. Okay. Next, at section 2, here, somewhere here, just before the applied load, it's R1x. Section 3, just after the applied load, that's R1x minus Px minus A. Then section 4, okay, after the support, or just before rather, the support reaction, or at the very end, it's R1L minus P times L minus A. Now, no need to dwell much on all of these. What I'd like to highlight lang here is that try to look at section 3 and section 4. They actually look the same. Okay? The form looks the same, but what can you notice? Section 4 is found at the very end of the beam. In section 4, the support reaction R2 was not already included. Correct? Now, this is the bottom line. Okay? Reactions and loads found at the very end of the beam are not included in the moment function. So if I have a support reaction, if I have an applied load at the very end of the beam, they are not included in the moment function. Okay? Is that clear? So that's what I'd like to highlight in this slide only. Okay. Now, here are the summary of steps in order for us to solve double integration method. Number 1, step number 0, automatically, our favorite step is to Draw the free body diagram and solve for the support reactions. The next step is to establish the origin and the positive direction, right? So you always establish the two. Origin is where x is equal to 0, and a positive direction. If to the left is positive, I need to define the end of the beam as the leftmost part of the beam. If the right is positive, the end of the beam is the rightmost end as well. Excuse me. Now, the positive direction is very important because we need to define the end of the beam. Meaning, from this point onwards, if my positive is to the right, if I say end of the beam, the end of the beam is the rightmost portion. Okay? Wrong spelling, sorry. Okay? And if the left is positive, and I mention end of the end of the beam is left. Are we clear with that? Next. For example, just to show you an illustrative example, examples, take for example these two. Step 0, solve for the support reactions. Okay? Step 1, establish the origin. Okay? For example, you want the origin for this problem to be here, okay? And to the right as positive. Okay? You are actually the one to solve or to determine where the origin and the positive direction is. But most of the time, in the exam, we normally set the positive direction and the origin para pare-pareho yung answers ninyo. And of course, to test whether you know, pag linipat-lipat namin yung origin and the positive direction, you still know how to answer the problem. So in this case, if I have a problem such as this, okay, the origin is at x, or where x equals 0 is at A. And since my positive direction is to the right, sabi natin, if to the right, the end of the beam is the rightmost end, it's B. Are we clear with that? Okay, next, how about this example? If I set my origin here, so x equals 0 at B, meaning C is equal to x equals 0.5, and A here is actually x equals -1. Are we clear with that? Next, I also define the positive direction as to the right, meaning, okay, go back here, if positive is to the right, okay, the end of the beam, so I need to define the end is actually the rightmost part. Okay? Next, step 2, write the moment function, okay, by describing the discontinuity function for each load. Now again, look at this. Please remember that if we have distributed loads, we need to perform dagdag bawas if it's not loaded up to the end. Now, please remember, what is our end again for this example if to the right is positive? It's actually B, correct? And you can notice that the distributed load is not loaded up to the very end. Therefore, I need to perform dagdag bawas, meaning I need to add, okay, such that the load, the distributed load, is loaded up to the very end, and it should look like what I have shown in the previous slides. But this is actually not the same to the original function, to the original load. Meaning, kung anong idinagdag ko hanggang sa pinakadulo, siya rin dapat yung ibabawas natin. So that's what we call a dagdag bawas method. I added this portion for it to be loaded up to the end, but I also need to bawas or to subtract the same, right, magnitude but opposite direction in order for me to return, right, to my original load. Is that clear? Of course, in this second example, no need to perform dagdag bawas because I don't have any distributed loads. Next, step number 3, I now need to write the moment function. Right? Now, step number 2, a continuation rather. Now, please look at this moment function over here. Now, I have mentioned that, please remember, ano ulit yung not, right? Not included in the moment function. We said that the concentrated loads, support reactions, applied moments, applied or found at the end of the beam are not included. So in this case, what's the end of the beam again? It's the right, which is B, sabi natin. So anything found at the right, so meron kang concentrated load na RB, hindi yan kasama sa moment function. How about in the second example? To the right is positive still. So sabi natin yung end ay nasa right, which is D. So hindi kasama yung 1.5 or the load found at the end of the beam. Okay? So this is now my moment function. Okay? D squared y over dx squared is 1 over EI. 16.8 is actually this one. It's positive kasi upward. X minus A. So A is equal to 0 because it's located at the origin. Raised to 1. That's my concentrated load. How about the distributed load? Going back to our código, our cheat sheet, it's omega over 2. So 16 over 2. Right? So 16 kilonewtons per meter. So omega over 2, 16 over 2. It's negative because it's downward. X minus A. A is still equal to 0 because it started at point A. Right? The distributed load started at the origin. Raised to 2. Right? Plus po yun because I now need to describe this one, right? Yung ibabawas natin. So this one is 16, right? The magnitude is still 16, right? 16 kilonewtons per meter all over 2. So omega naught over 2, 16 over 2. X minus A. So A, where did the uniformly distributed load start? A is equal to at X equals 1.5. That's X minus 1.5 squared. Next, how about the second example? For the second example, again, the end is, since to the right is positive, the end is the rightmost portion, or letter D, 1.5 kilonewtons. Okay, so we don't include this one. Okay, so D squared Y all over dx squared is 1 over EI times, right, 6.75. Look at this. That's the applied moment or the support reaction na moment. It's counterclockwise. So look at our cheat sheet again earlier. Counterclockwise. So this is negative. Negative 6.75 X minus A. So what is A again? A is the location. Since my origin, I established that the origin is found here. Right? So the location is actually negative 1. Correct? So if this is X equals 0, this is X equals negative 1. Okay, so X minus negative 1, I get X plus 1 raised to 0 because that's an applied moment. Plus 4.5 because the support reaction is upward. X minus A, but A is the location of the concentrated load. Okay, so it's found at X equals negative 1 again. So if this is X equals 0, this is found at X equals negative 1. So X minus negative 1 raised to 1 because that's a concentrated load. Then, how about this one? Minus 1.5 kasi pababa yung load. X minus 0. Why X minus 0? X minus A. But this load is found at the origin. So it's actually at X minus 0. Then this one, 1.5 X minus A, it's located at X equals 0.5, so to the right. So X minus 1.5 raised to 1. Oops, I have a mistake over here. Okay? Minus 1.5 X minus 1 raised to 1. I am sorry, but this portion, okay, this one over here should not be included. Okay? So again, why? I'm sorry for that mistake. So I need to cancel this one. Right? So because this 1.5 kilonewton load, sorry, so that's a common mistake. This is found at the end of the beam. Therefore, it should not be included. Is that clear? Okay, so I apologize for that mistake. Okay, questions? Okay, so we need to delete that one. Then, I now need to perform double integration, right, to get the slope and to get the deflection of the beam. So please remember, if I integrate once, I get the slope plus a constant integration. constant of integration C1. Then I integrate further. I now have two constants of integration, C1x plus C2. Next, after integrating twice, I now apply my boundary conditions to solve for the constants of integration, C1 and C2. Okay. So what are, to be able to solve for the constants of integration, again, this is a pin and this is a roller. What are our constants of integration? I can say that if there's a pin, I can say that the deflection at the pin, or x equals 0, since that's the origin, is equal to 0. What else? I have a roller. I can say that if I have a roller, the deflection at the roller, or at x equals 2.5, is equal to 0. How about this second example? What are my boundary conditions? I have a fixed support. So for my fixed support, I can say that the deflection, delta y, at x equals -1, yx equals -1, because we established that this is our origin. So the fixed support is at a distance -1. So the deflection at x equals -1 is equal to 0. And since that's a fixed support, the slope theta. So again, only for fixed supports, the slope theta at point A, where x is equal to -1, is also equal to 0. So I impose these boundary conditions in order for me to solve for the constants of integration C1 and C2. After that, I should now be able to solve the problem. Okay? I hope you understood the concepts and the summary. Let's try to look at this example. Please read the example. I'll first have a water break. Okay. A simply supported beam is subjected to the load as shown. We are being asked to determine the slopes at point A and at point B. So what is theta at A and B? Okay. So this is a simply supported beam. I have a pin and a roller rather, and a pin. So I know that the slope is not equal to 0. And the displacement at point C. The flexural rigidity EI is constant, and we're being asked to use the reference section indicated, so which is this one. Okay? So meaning, it's already set in the example that my origin, or my x equals 0, is at point A. So this is x equals 0, and the positive direction is to the right. Okay? So what does that mean? Okay? So let's try to solve this example first. Okay. So before that, please get a copy, because I'll solve the example. Please try to get a copy or a snapshot of the problem. Okay. I'll solve the problem so that you can follow. Okay, so let's try to solve the example. I hope you have a copy of the example right now. You won't be able to see the example I'll be writing. So please get a copy. Please secure a copy of the example right now. Okay, so our step 0 is use equilibrium to solve for the support reactions. So since I have a simply supported beam, kindly just show at home that the support reactions AY is actually 66.75 kilonewtons upward. Please pardon my bad handwriting. And BY, or the reaction at the roller or at the pin, is equal to 59.25 kilonewtons, also upward. Then we mentioned that we need to establish the coordinate system. Okay? So I need to establish the coordinate system, and it's already dictated in the problem, forced in the problem. The origin where x equals 0 is actually at point A. Okay? And it's mentioned in the problem that our positive direction is to the right. Now, going back to our reminders, if I have a positive direction to the right. What is my end? Okay? The end, therefore, is B. Okay? Are we clear with that? Okay? Questions so far? Clarifications? Okay. Next, step 2, write the moment function. Okay. Now, it's mentioned here that we mentioned that the force reaction By is not included since it's found at the end. Now, again and again, any support reaction, any force, any applied moment found at the end, in this case, which is B, okay, is not included in the moment function. Therefore, what are forces or found at the end of the beam? It's only the force reaction By, so it's not included. Then, look at the second reminder. Do I need to perform dagdag bawas? I actually do not need to perform dagdag bawas. Why? Because the distributed load is actually loaded up to the very end of the beam. Okay? Therefore, I can now write my moment function. Okay? So my moment function is d squared y over dx squared is equal to 1 over ei, okay, multiplied by, again, the first one is the support reaction. So I have ay, which is 66.75 upward, so that's positive. 66.75 x minus a, but where is the location of the support reaction? It's at x equals 0, so that's 0. Raised to, that's a concentrated load, raised to 1. Okay? Next, how about the uniformly distributed load? Okay? So it's omega over 2. So it's the magnitude or the intensity is 12 kilonewtons per meter, omega all over 2. Okay? Then the load is downward, so negative. X minus A, where is the start of the uniformly distributed load? It's found at x equals 0. That's correct. Uniformly distributed load raised to 2. Okay? Then lastly, I have a concentrated load, a 30 kilonewton concentrated load, which is downward, so that's negative. X minus A, the location of the concentrated load is at x equals 3 raised to 1. Okay? So that is my moment function. So if I now have my moment function, what I can do is I can now perform double integration. Okay? So to perform double integration, I can say that if I integrate my moment function, I should be able to get the slope. dy over dx is just equal to, so I just integrate the first term, 66.75 all over 2 x minus 0 squared, minus, so that's 12 over 2 is equal to 6. 6, then I integrate 6 all over 3 x minus 0 cubed minus 30 all over 2 x minus 3 raised to 2 plus the constant of integration, C1. Then I integrate further. Okay? I now have the equation of my elastic curve. Okay? So let me call this one the slope equation as equation A and the deflection equation as equation B. Okay? Then I now apply the boundary conditions to solve for C1 and C2. But please remember, it's stated here that if the value inside the bracket is negative, the value becomes 0. So what are our boundary conditions again? Please remember that our boundary conditions are, please remember, I have a pin and a roller. So I can say that, what's the first one? Please help me. It's actually the deflection y is equal to 0, where at x equals 0. So at the roller support. Okay? So I can say that from equation B, so from equation B, I can say that, so this is equation B over here, I can say that y is equal to 0 is equal to, I just substitute 1 over ei from equation B times 33.375 divided by 3 is actually equal to 11.1 11.1125, okay? 11.125 rather. X minus 0. So x natin, we mentioned that x is equal to 0. So x minus 0, so 0 minus 0 raised to 3 minus 2/4. So I am just copying here. So 2/4 is 0.5. X minus 0, again, x is equal to 0 raised to 4. 15 all over 3, so minus 5. 0 minus 3 cube. So x is equal to 0. Plus C1 times 0. Okay? So since x is equal to 0, plus C2. Okay. Therefore, in this case, what I can do is 0 minus 0, cancel. 0 minus 0, cancel. 0 minus 3, that's negative. So inside the bracket is negative, that's automatically equal to 0. C1 times 0, that's also equal to 0. Therefore, I can say that C2 is equal to 0. Okay? What's our next boundary condition? So my next boundary condition, I can say that I have a pin at the end. So I can say that y is equal to 0 at x is equal to, okay, x is equal to, so at the location of B, x is equal to 8. Okay? Therefore, similarly, from equation B, okay, since I'm looking at y, okay, so from equation B, I can say that y is equal to 0, is equal to 1 over EI, okay, times 11.125 x minus 0. So again, my x is actually equal to 8. 11.125, 8 minus 0 cube minus 0.5, 8 minus 0 raised to 4 minus 5, 0 minus, 8 minus 3 raised to 3 plus C1 times x, which is 8, plus C2, which we already know is equal to 0, as we have solved over here. Okay? Now, I can say here that I can cancel nothing, actually. Okay? Because 8 minus 0, that's positive. 8 minus 0, that's positive. 8 minus 3, that's positive. Okay? So yung 0 lang dyan, then C1 times 8. I can now solve for C1. I equate everything to 0. I can say that, kindly solve and show that C1 is negative 377.875. So of course, here you get a value here. Okay? So again, this entire thing is equal to 0. Okay? Questions? Okay. Now, I can now solve the problem since I already know the boundary condition C1 and C and solved for C1 and C2. Okay? So the first problem, the first question I think is we're being asked for the slope at A. Okay? So we're being asked what is dy over dx? So what is dy over dx? Okay? At x equal to 0. Okay? Or at A. Okay? So I will use equation A. Okay? So from equation A. Why do I need to use equation A? Going back, I need to use equation A because I'm solving for the slope dy over dx. Are we clear with that? Okay? So going back, okay, I'll just make this smaller para mas nakikita natin. Hopefully, you can follow. So equation A, dy over dx, this is just equal to 1 over EI times, so go back, 66.75 over 2 is 33.375. X minus 0, so again, I am looking at x equals 0 because I'm observing at A. 0 minus 0 squared minus 6 all over 3, that's 2. X minus 0, so 0 minus 0 cubed, minus 30 all over 2, that's 15. 0 minus 3 squared. I'm sorry, my handwriting is not that good. Minus plus C1, and we have already solved C1 to be equal to negative 377.875. Okay? Now, I need to evaluate, but again, 0 minus 0, cancel. 0 minus 0, cancel. 0 minus 3, Okay? This will also cancel out because that's negative in value. Okay? So ang naiiwan na lang natin is negative 377.875. So my final answer here is negative 377.875 all over EI. Okay? So what is the unit of measurement over here? Since I didn't convert any value of my forces, okay, please remember that if I have slope over here, your numerator would be force. Okay? So I didn't convert anything. Force times length squared. Okay? Why? Because EI is actually, E is megapascals or a unit of pressure times I, which is length to the fourth, okay, which will leave us with force times length squared. So if I divide the two, it becomes radians. Okay? So unitless. So remember, for slopes, the numerator is force times length squared. I didn't convert anything, so it's the force is kilonewtons and the length is in meters. Okay? So since I have a negative answer, I can say that's 377.875 all over EI clockwise. Okay? This is now my final answer. Okay, next, let's continue solving. The second item, we're being asked for the slope at point B. Okay? So the slope at point B or at the very right end. So what is dy over dx? Okay, so what's dy over dx at x is equal to 8 or at B? Okay, so this is just equal to, again, we'll just substitute 1 over EI. Again, I'm using equation A. Why equation A? Because I'm solving for the slope. Okay? So dy over dx, that's still 33.375. X minus 0, so that's 8 minus 0 squared. Remember, I'm using x equals 8 minus 2. Okay? X is still 8 minus 0. I'm just substituting from equation A, cube, minus 15 times 8 minus 3 squared, minus 377.875. If you'll notice, well, I need to evaluate everything because the values inside the bracket are actually all positive. So I need to evaluate. Hence, if I evaluate everything, kindly prove that that's equal to 359.125 all over EI. It's still a slope, so the unit of the numerator is force times length squared. Okay? I get a positive answer. Therefore, this is counterclockwise. Okay? Questions? I hope I'm not going too fast. Next, last item, we're being asked for the deflection at C. Okay? So lastly, we're being asked for the deflection at C. So for the deflection, okay, y, what is y? At x equals 3. Okay? I think we're being asked at point C. Okay? So I am now substituting or I am now using solving y at x equal to 3. So of course, I need to use equation A because I'm solving for the deflection. Okay? So I'm using equation B rather, since I'm solving for y. Are we clear? So we substitute, we use this equation over here, equation B, okay? But substitute x equals, where is that? Where is that? X equals 3 to this equation over here, equation B, okay? So together now, 1 over EI times 11.125 x minus 0, that's 3 minus 0 raised to 3, minus 0.5, 3 x minus 0 raised to 4, minus 5, x minus 3 or 3 minus 3 raised to 3, minus C1x or plus C1x, 377.875. Okay, sorry, 377.875 times x equals 3 plus C2, but C2 is just equal to 0. Okay, so no need. Now, in this case, I can cancel 0, of course, and 3 minus 3, that's 0. Then I can evaluate. I can now say that the deflection here is, please evaluate this one, okay, negative 873.75 all over EI. But be careful, what's the unit of measurement? Okay? So since this is a deflection, please remember that the unit of measurement of deflection is length. Okay? Therefore, here, the numerator should have force times length cubed. Okay? Because if I divide it by EI, which is force length squared, I am only left with a unit of length. Okay? I get a negative answer, therefore that's 873.75 all over EI, negative, so downward. Any questions so far? Any questions? Okay, so that is example 17.2. Okay, so I hope you were able to absorb example 17.2. Okay, let's go back to the example. Okay, so that's the problem. Okay, so please absorb first. Let me have another water break. Okay. Let's now look at another example. Okay. For the cantilever steel beam, where E is 200 gigapascals and I is 410 times 10 to the 6 millimeters to the fourth, okay, use double integration method to determine the deflection at the free end C. However, okay, let's have a twist for this example. Let's use different reference sections. Okay? So meaning, I'll transfer the origins and I'll transfer the positive directions. Okay, are we clear? Okay, so again, at this point in time, kindly get a copy of this example. Okay? Have a snapshot of this example, okay, while I transfer and solve. Okay, so let's now solve example 17.3. Okay, so example 17.3. Okay. So I hope you now have a copy of the figure and the problem. If not, please do so. Okay, so let's now solve equilibrium. Kindly show at home. Since that's a fixed support, I know that the support reaction is actually a force, AY, 130 kilonewtons upward. And the moment reaction, since that's a fixed support, is 335 kilonewton meters counterclockwise. Okay, let's solve the problem first using our typical coordinate system. So step 1, the origin is where x is equal to 0. Let's say that I will set the origin at A. So my x equals 0 is at A. Then, conventional muna, our positive is to the right. Okay? Therefore, if my positive is to the right, what is the end? Try to answer. Okay, so the end is actually C. Very good. Okay? Questions so far? Okay, next, we now write the moment function. Okay, so look at this one. Now, again, if my end is C, anything found at the end is not included. So what is the load, or what are loads found at the end or found at C? It's only the 40 kilonewton force. So the 40 kilonewton force is not included in the moment function. Next, yes, I need to perform dagdag bawas. Why do I need to perform dagdag bawas? Because the distributed load is not loaded up to the end. Are we clear? Sir, before we continue, what if it doesn't start at x equals 0? It's okay. What's important is the distributed load is loaded up to the end. Okay? So we perform dagdag bawas. Okay? So my dagdag bawas would be something like this. Okay? I need to complete everything, okay, up to the end. Okay? But whatever I added, okay, I also need to remove. So I added this load over here. So I also remove the same magnitude but opposite direction. Okay? So I can now write my moment function. So my moment function would be, by the way, I have, just to write, I have 130 kilonewton force there, and I have a 335 kilonewton meter support reaction. Okay? So I can say that d squared y over dx squared is equivalent to 1 over EI, right? Times, let's start with the 130 kilonewton load, 130, positive because it's upward, minus 0 raised to 1, right? This this support moment, moment reaction is 335, positive or negative. It's counterclockwise, so that's negative. X minus 0 raised to 0, okay? So it's at x equals a. So ang origin natin, we mentioned that this is our origin, and to the right is positive. Minus 30 over 2. What does 30 over 2 mean? Okay? So 30 over 2 is actually, right, the uniformly distributed load, that is downward, so omega over 2. X minus a, it started at 0, okay, raised to 2. Next, how about yung ibabawas natin? Okay? So plus this one, okay? So this portion over here, okay? Plus 30 all over 2, plus because it's upward, omega over 2, so 30 over 2. X minus a, where did it start? X minus a, so a is actually 3. Okay? So the distributed load started at 3 raised to 2. Okay? That's raised to 2. Then I can now perform double integration, okay, in order for me to find the slope. Okay? So double integration will tell me that this is equation A. Okay? So don't forget C1. Okay? Please double check if my integration is correct. Then I integrate further. I now get equation B, which is the equation of the elastic curve. So this is the equation of the elastic curve. Kindly double check. So please take note, I have a constant of integration, C1x and C2. Next, I now need to apply my boundary conditions to solve for C1 and C2. Note that if the value inside the bracket is negative, the value becomes 0. Okay? So what are the boundary conditions? Okay? Again, boundary conditions, I need to look at the support reaction. Okay? So since that's a fixed support, I can say that, number 1, dy over dx, fixed support. Okay? Go back to our material for support reactions, for boundary conditions rather, dy over dx equals 0, where at x is equal to 0. Okay? Therefore, from equation A, since I'm looking at dy over dx, I can say that dy over dx is equal to 0, is equal to 1 over EI times, okay, I'm looking at equation A, 130 all over 2, that's 65. X minus 0, so again, I'll just substitute x equals 0. Okay, 0 minus 0 raised to 2, minus 335, 0 minus 0 raised to 1, minus 15 all over 3, that's 5, okay, times 0 minus 0 cube, plus 5, 0 minus 3 cube, okay, plus C1. Okay. Then look at this, 0 minus 0 cancel, 0 minus 0 cancel, 0 minus 0, cancel. 0 minus 3, that's negative. So that's canceled also, which tells us that C1 is equal to 0. Okay? Next, boundary condition. What's the next boundary condition? That's a fixed support. Aside from the slope being equal to 0, I can say that the deflection is also equal to 0, where still at x equal to 0, where you have a support reaction. So y is equal to 0. I now use equation B right here because I'm solving for the deflection. Okay? So y equals 0 is equal to 1 all over EI times 65 over 3, 0 minus 0 cube minus 335 all over 2, 0 minus 0 squared, minus 5 all over 4, 0 minus 3 to the fourth, plus C1, which is just 0. We already solved it to be equal to 0, times 0, plus C2. Okay? Therefore, we can say that 0 minus 0, cancel, cancel, 0 minus 3, cancel, 0 times 0, cancel, times C2. So I can say that C2 is now equal to 0 also. Then I can now solve for the problem. Recall that E, the modulus of elasticity, is 200 gigapascals, and the moment of inertia is equal to 410 times 10 raised to 6 millimeters to the fourth. Okay? So from equation B, since I'm solving for the deflection at the free end, right? So I can now say that from equation B, y, okay, so what is y at x is equal to, so what's x if I'm looking at the free end? X is equal to, correct, x is equal to 5, or at C, because that's what I am looking for. Okay, let's just substitute the values using equation B. That's 1 over EI times, so equation B, let's just substitute 65 over 3 times 5 minus 0 cube minus 335 all over 2, 5 minus 0 squared minus 5 all over 4, 5 minus 0 to the fourth, plus 5 over 4, 5, okay, minus 3 raised to 4. So I'm just copying equation B but substituting 5, okay, dun sa ating value of x for the value of x, plus C1x, C1 is 0, plus C2, which is also equal to 0. So everything here is positive, so I need to evaluate. And okay, please remember that everything inside the bracket is positive, so evaluate. Once I evaluate, I get an answer of negative 26,885 all over 12 all over EI. Now, please take note that I didn't convert anything, and this is a deflection problem. Therefore, the unit of measurement for the numerator is force times length cubed. Okay? So let's substitute. Again, as you know, I'm not sanay with any other unit of measurement. E is just 200,000 megapascals. So that's Newton per mm squared. And I is 410 times 10 to the 6 mm to the fourth. So I need to convert kilonewton meter cube, okay, into Newton millimeter cube. Okay, so how do I do that? To convert kilonewton meter cube into Newton millimeter cube, I just need to multiply this by 1,000 raised to 4. Okay, so that's Newton millimeter cube. My final answer, kindly confirm, is negative 27.3 mm or 27.3 millimeters. Ooh, the arrow is there, downward. Okay? Questions? Clarifications? Okay. Now, let's repeat the problem again, but let's make it more interesting. I'll now transfer the origin and the positive axis. Now, what if I want my What if I want my origin or my x equal to 0 at, let's say, how about at C? Okay? So if it's at C and my positive direction is to the right, okay, what is the end? Again, positive to the right, what is end? Okay, the end is still C. Very good. Okay? But again, still, the origin, x equals 0, is also found at C. That's okay. Now, we write the moment function. Now, please remember, the 40 kilonewton force is still not included primarily because it's found at the end. Okay? Do I need to perform dagdag bawas? Yes, I need to perform dagdag bawas because the distributed load is not loaded up to the end. So to perform my dagdag bawas, okay, I do that one and reduce. Okay? I remove rather kung anong idinagdag ko. Don't forget, I have a force, 130 kilonewton force and a 335 kilonewton meter support reaction. Okay? I think there's a truck roaming around giving some announcements about the enhanced community quarantine. So I do apologize. Okay? Now, okay, I can now write the moment function. So the moment function here is d squared y over dx squared is equal to 1 over ei. Okay? Let's start with the 130 kilonewton applied force, 130 x minus a. But then again, where is my origin? Remember that my origin is at C. We have established that. And to the right is positive. Therefore, where is the location of the 130 kilonewton force? It's at -5, correct? Therefore, x minus -5, so that's x plus 5 raised to 1 minus 335 because the applied moment is counterclockwise. X minus a, where is the location? It's a is equal to -5, so x minus -5, x plus 5 raised to 0. How about the distributed load? That's 30 all over 2. It's negative because it's downward. Times x minus a, or x minus -5. So x plus 5 raised to 2 plus 30 all over 2. This one. Okay. Where did it start? Okay. So that's a challenge. The uniformly distributed load started here. Okay, so that's actually x equals -2. So x minus -2, x plus 2 raised to 2. Okay? Then, I now perform double integration. Okay? Double integration, that's the slope. Okay? Then, double integration again. Okay? This is now, this is now the deflection. Okay? After which, I now need to perform or impose my boundary conditions. Okay? So to impose my boundary conditions, take note that that's a fixed support. Therefore, ganun ulit. dy over dx is equal to 0. But where? dy over dx is 0 at the fixed support where x is equal to -5. Okay? So from equation A, so I'll just show this. From equation A, right here, okay, I can say that dy over dx is equal to 0, is equal to 1 over ei. Let's just substitute everything, but I'll use x as -5. Okay, so just substituting, this will now give me 65. Okay, 130 all over 2 is 65 times -5 plus 5 squared minus 335 times -5 plus 5 raised to 1 minus 5 times x plus 5, so -5 plus 5 raised to 3 plus 15 all over 3, 5 times -5 plus 2 cube plus C1. Okay? Then Look at the brackets. Negative 5 plus 5, that's 0. Negative 5 plus 5, that's 0. Negative 5 plus 5, that's 0. Negative 5 plus 2 will yield a negative answer. Therefore, this is also 0. Okay? Therefore, C1 is actually equal to 0. Next, boundary condition. That's a fixed support. Therefore, I can say that y is equal to 0 where? At the fixed support, x equals negative 5. Okay? Therefore, I can say using equation B, okay, y is equal to 0 is equal to 1 all over EI times, I'll just substitute in equation B, but I'll use x equals negative 5. That's 65 all over 3. Negative 5 plus 5 cube minus 335 all over 2. Negative 5 plus 5 squared minus 5 all over 4. Negative 5 plus 5 to the fourth plus 5 all over 4. Okay, where am I? 5 over 4 times negative, I'm just substituting 5 plus 2 to the fourth. Okay, plus C1, which is 0, times x, which is negative 5, plus C2. Okay, let's evaluate. 0, 0, 0. Negative 5 plus 2, that's negative, so it's 0, 0. Therefore, C2 is still equal to 0. Okay, now let's continue and solve the problem. I can now solve the problem. I'm now solving what is y. Okay, so what is y at x is equal to? Sige, I'm solving for, remember, what is the deflection at the free end. But in this problem, in this scenario, okay, my origin is also at C. Therefore, it's actually at x equals 0. Okay? Therefore, this is now equivalent to 1 over EI times, I'll just substitute and use equation B right here. Okay? Equation B, because I'm solving for the deflection. Let me just minimize so that you can see. Okay? But please remember, I'm substituting x equals 0. Okay? So let's just substitute. This is just 65 over 3. I'll just copy everything but use x equals 0. So 0 plus 5 cubed minus 335 all over 2. 0 plus 5 squared minus 5 all over 4. 0 plus 5 to the fourth plus 5 all over 4. 0 plus 2 to the fourth plus C1 x, but that's 0 and C2. Okay? Therefore, if I now evaluate this one, this is equivalent still to, if I evaluate this one, this is still equivalent to negative 26885 all over 12, okay, kilonewton meter cube all over EI. Okay? Then again, to convert everything into Newton millimeter cube, I multiply this by 1,000 to the fourth Newton millimeter cube all over 200,000 times 410 times 10 to the sixth. This is still equal to, yay, we have shown it's the same, 27.3 millimeters downward. Okay? It's the same as our previous solution. Okay? Last, one more. What if my origin, okay, is, or where x equals 0, okay, is still at C, so it's at the free end. That's where x is equal to 0. So, but my positive direction in this case is, okay, to the left. If my positive is to the left, what is the end of the beam? It's the leftmost part. The end is A. Very good. Okay, it's the left. Now, we write the moment function. However, please take note, if my origin, or where x equals 0, is actually at C, so this is where my 0 is, and positive is to the left, that changes the entire problem because what is the end of the beam? It's A. Therefore, if the end of the beam is at A, okay, The support reactions AY and MA are not included because, as we have mentioned, they are found at the end. Okay, so anything found at the end is not included, and our end is at A, so the support reactions are not included. What else? Do I need to perform dagdag bawas? Actually, no. We do not need to perform dagdag bawas because the distributed load is already loaded up to the end. Oops, it's already loaded up to the end. Now, right? Why is it already loaded up to the end? I can show you, or we can see that the end is at A. Okay? So it's already found that the load is already loaded up to the end, or already found, okay, until, okay, the end of the beam, which is at A. Okay? So therefore, how about the 40 kilonewton load? It's now included. And because it's not the end, point C is not the end. It's actually the start. Therefore, I can now solve the problem and write, rather, the moment function. Okay? Our moment function here is actually d squared y over dx squared is equal to 1 over EI, the 40 kilonewton load, that's downward, negative 40, x minus 0, because it's raised to 1, because it's found at the origin. How about the 30 kilonewton meter load? That's omega over 2, 30 all over 2. It's negative because it's downward. Okay? Times x minus a. Where is the location? Okay? It started at, if this is 0, taking to the right as positive, it started at x equals 2. So x minus 2 raised to 2. That is now the moment function. It's very short. Okay? So sometimes it's important that we can select the right reference section para mas madali yung moment functions natin. Then, I can now perform double integration from that equation. To integrate first, that's the slope. Then, I integrate further to get the deflection. Okay? So these are now with my constants of integration, C1 and C2. I apply my boundary conditions to solve for C1 and C2. Now, please be careful. If I am now applying my boundary condition, okay, what's the first boundary condition, people? I have a support reaction. Okay? So I can say that dy over dx, I have a fixed support rather. Fixed support, so slope is equal to 0. Okay? Where? At the fixed support, but in this problem, it's located at x equals 5. Okay? So it's found that x equals 5 because, again, going back, this is x equals 0, then going to the left as positive, this is x equals 5. Okay? So from equation A, since I'm using that, dy over dx is equal to 0, okay, I'll just copy equation A, but, I'll just copy equation A, but I'll substitute, okay, or I'll use x is equal to 5. Okay? So that's 1 over EI times negative 40 all over 2. So that's negative 20. 5 minus 0 squared minus 15 over 3, which is 5, times 5 minus 2 cubed plus C1. Okay? Obviously, they're not negative, so I need to evaluate. Okay? C1 is actually equal to, kindly confirm, 635. Okay? Next, boundary condition. I can say that y is equal to 0 because that's a fixed support. Okay? Y is equal to 0 where? Still at x is equal to 5. Okay? So I now use equation B. I just substitute. Y is equal to 1 over EI times, I just copy everything, negative 20 all over 3, but use x equals 5, okay? Minus 5 all over 4, 5 minus 2 to the 4th, plus C1 is 635, so plus 635 times 5, so C1x plus C2, okay? Obviously, no negative answers in the brackets. Therefore, I need to evaluate. I should be able to get C2 is equal to negative 26885 all over 12. Okay? I can now solve the problem. Okay? I can now solve for y. So what is y? Okay? So I'm solving y at x is equal to at the free end. So the free end is actually where x is equal to. In our problem, in this scenario, it's where x is equal to 0 or at c, at the origin. Okay? So I'll just substitute x equals 0 in equation B still. Okay? So still in equation B right here. Okay? So let's just substitute everything. I now have 1 over EI times, but I'll use x equals 0, negative 20 all over 3. 0 minus 0 cube minus 5 all over 4. 0 minus 2 to the 4th plus C1. Okay? So plus 635 times x, which is 0, plus C2, which is negative 26885 over 12. Okay? Then I evaluate. Okay? Please take note. Okay? Look at this. 0 minus 0, cancel. 0 minus 2, that's negative, so cancel. 635 times 0, cancel. So I am left with, as you can already predict, the same answer, negative 26885 all over 12 all over EI. Okay? So once I substitute everything, this is negative 26885 all over 12 times 1,000 to the 4th para maging Newton mm cube. Okay? All over 200,000 megapascals times 410 rather times 10 to the 6 mm to the 4th. Okay? This will give me negative 27.3 mm, or final answer 27.3 millimeters downward. Okay? I have a horrible handwriting. So that is how you solve problems, right? If we are dealing with different reference sections. So those are some examples of how you can solve or use the double integration method. I hope you were able to understand, right? These examples. I hope you were able to understand the concepts. Now, just to show you, those are the remaining examples. I have 2 more practice problems. So at home, you can actually try to solve this first practice problem with the given answers already, and this second practice problem. Okay. That's the end of our lecture for double integration, the first part of the double integration method lecture. If you have concerns, you know how to reach me. You can reach me through email or you can send me a private message. And please do not hesitate to ask if you have problems. Okay? That ends our lecture for today.